Okay, let's talk about LEDs. They are literally everywhere, right? In your phone, your car, your house, everything. And we have this idea that they're these perfect little engines of efficiency, just taking electricity and turning it straight into light. But if they're so perfect, that leads to a really interesting question.
I mean, you'd think it's simple. More power in, more light out. A nice straight line on a graph. But that's not what happens. As you pump more and more current into an LED, the brightness kind of starts to level off. It hits a ceiling. This is called saturation. And to really get why this happens, we have to forget the real world for a minute and start inside a perfect imaginary one.
So, to crack this mystery, we first need to understand how an LED is supposed to work, in theory. We've got to go right to the source, to the very moment a tiny particle of light, a photon, is born. Deep inside the heart of an LED, there's a semiconductor material. And when you send an electrical current through it, electrons combine with their opposites, which are called holes. When they meet, bam, a photon is created. The speed at which this happens, how many photons are being born every second, is what we call the internal photon flux. Think of it as the raw, pure light being created inside the chip itself.
And in this perfect world, the relationship is super simple. The optical power you generate is directly proportional to the current you inject. It's almost 100% efficient. You push one electron in, you get one beautiful photon out. It's linear, it's predictable, it's perfect. But, as you know, we don't live in a perfect world.
See, creating a photon is just step one. The real challenge, the true adventure for our little particle of light, is getting out of the LED. And that journey is tough. It's like a gauntlet of obstacles, and each one chips away at that perfect efficiency we just talked about. Before a photon even gets a glimpse of the outside world, it faces two huge threats. First, it can just get swallowed back up by the material it's traveling through, turning its light energy back into useless heat. Bummer. Second, if it actually makes it to the surface, it can bounce right back inside, kind of like seeing your reflection in a window. These two things immediately start knocking down our efficiency.
But the biggest obstacle by far is something called total internal reflection. Because the LED material is way more optically dense than the air outside, light can only get out if it hits the surface almost perfectly straight on. If a photon comes in at too steep of an angle, it's trapped. It gets reflected back inside as if it hit a perfect mirror. This creates a really narrow escape cone. And this right here is the heart of the problem. Photons are created going in every possible direction, completely at random. But only the lucky few that happen to be pointed inside that tiny escape cone actually make it out. The vast majority of the light we just work so hard to create is trapped inside.
So, how small are we talking? Well, the math gives us a rough idea. That N you see is the refractive index of the material, and it's usually a pretty big number, like 3 or 4. Well, if you square that and multiply by 4, you end up with a huge number on the bottom of that fraction. What it means is that maybe only 2% or even less of all the photons created can escape on their first shot.
Now, it's not totally hopeless for these trapped photons. There's this really cool process where a trapped photon can get reabsorbed, which creates a new electron-hole pair, which can then combine to spit out a brand new photon. This new photon gets its own random direction, giving it another roll of the dice to try and hit that escape cone. It's called photon recycling, and it helps a little, but the main problem is still there. Okay, so all of this brings us right back to where we started. What does this whole escape problem have to do with the LED getting less bright when we crank up the power? And here it is again, that saturation curve. We start off on that beautiful straight line from our perfect LED world. But then, it just bends over. The efficiency plummets. We're jamming more and more electrical traffic in, but the light output just can't keep up. It's literally an LED traffic jam. So why does this traffic jam happen? The source material points to 3 main culprits. These are the bad guys that show up at high currents and just steal our light. All right, let's unmask these culprits. The first one is simple: heat. When you push a ton of current through the LED, it just gets hot. That's Joule heating. And a hotter LED is just a less efficient LED. But there's a sneakier problem called carrier leakage. Think of it like this. At low currents, every electron finds a hole and makes a photon. But when you crank the power, things get crowded. Some electrons just get shoved right past the light-making zone. They leak through without ever creating a photon. They add to the current, they add to the heat, but they don't add to the light. And this problem gets worse and worse the more current you add, which is exactly why that curve flattens out.
So we've seen all these different ways an LED can fail to be perfect. Photons get trapped, electrons sneak past without doing their job. So how do we boil all of this down into one single number that tells us how good an LED actually is?
Well, engineers use a metric called responsiveness. This is the bottom line. It answers a very simple question. For every amp of current we put in, how many watts of light we actually get out? This is the real-world performance number, taking into account every single loss we've talked about.
And here's the formula that wraps it all up in a neat little bow. See that A to X? That's the external efficiency, and it's really the hero of our story. It bundles together everything, the internal efficiency, all the losses from photons getting trapped, and that all-important escape cone problem. The key takeaway is that this one simple equation tells the entire story of light's journey, from a simple electron all the way to a photon escaping into the world.
And that brings us to the big final question. We've just mapped out all the reasons LEDs aren't perfect, we know light gets trapped inside, and we know that heat and leakage kill efficiency when we push them hard. So the question for the next generation of scientists and engineers is, how do we fix it? How do you design a surface that lets more light out? How do you build a material that stops those electrons from leaking? You see, understanding all these limits isn't the end of the story, it's the blueprint for building the perfect LED of the future.